Good evening, everyone. Welcome to the live problem solving session on GATE Metallurgical Engineering. These live sessions are brought to you in association with NPTEL and PMRF TA-ship. So, these live sessions will be happening every week on Thursday from 6 p.m. to 7 p.m. And if you are planning to attend GATE Metallurgical Engineering 2023, please do attend these sessions and at the same time encourage your friends also to attend. So, as part of these live sessions, we will be having problem solving sections, and at the same time, we will be having brief discussions on the topics related to the particular question that is being solved. So, in that case, if you follow these sessions regularly, you'll be getting an overall layout of how the syllabus is, and at the same time, you will be improving your problem solving skills. So, please do try to attend these sessions. So, for our first session, let me now start presenting my screen. I hope it's visible to all of you. Yeah, seems okay. So, this is our first problem solving session, and I am Santhya Krishnan. I am a PMRF research scholar at Soft Matter and Complex Fluids Lab, Department of Metallurgical and Materials Engineering at Indian Institute of Technology, Madras. So, after each session, if you find any additional doubts or if you feel that you need clarity on certain topics or you have any suggestions or feedback, please do email me at santhra.pmrfiatm@gmail.com. So, now let us move on to the first question of the first session. So the first question is, beach marks are commonly observed on the fractured surfaces of metals after a creep test, a fatigue test, an impact test, or a compression test. So this was asked in GATE Metallurgical Engineering 2019, 1 marks. So, before we jump into the answer of such a question, let us see what are the common fracture surfaces and fractographs for different materials under different loading conditions. So, the first case that we are going to discuss is ductile failure in tension. So, ductile failure in tension implies that the material under consideration or the specimen under consideration is a ductile specimen and we are subjecting it to a tensile load or a pulling load. So if you see the fracture surface, we can see cup and cone shaped fracture surfaces with a lip. So this is what happens to a ductile material when it is pulled. And if you observe this particular surface under a microscope, we will be seeing these kinds of images. These are known as dimples, or these cup-like depressions are known as dimples. So what are these dimples? These dimples are actually micro voids that come together. And there are two fractographs here actually. B is transgranular ductile fracture, that is, it is happening across the grains, and C is intergranular ductile fracture, that is happening through the ground boundaries, that is intergranular. So then you might be wondering what this final image is. So we have already understood that ductile failure in tension will give rise to cup-like depressions called dimples, and it will have a cup and cone fracture surface. So then what is this thing? This is torsion failure. When such a material is subjected to a torsion force, we can see that the dimples that were there, it becomes somewhat elongated. These elongated dimples are known as skewed dimples. So please keep in mind that ductile failure in tension will give rise to dimples, and skewed dimples can be obtained in case of torsion failure. So I hope this is clear to all of you. Now moving on, brittle failure in tension. Now what happens if the material under consideration is a brittle material and we are subjecting it to a tensile force? So if we see figure A, we can see that there is a riverbed like pattern, and this riverbed like pattern is obtained in transgranular brittle fracture, and if it is an intergranular brittle fracture, it will be having a grainy appearance. So that is about the fractograph of brittle failure in tension. And also we have already seen that in case of ductile materials, it will give a cup and cone like structure, right, at the fracture surface. But for a brittle material, when we are subjecting it to tension, it will have a perfectly flat and that will have a perfectly flat surface that is perpendicular to the applied load. So that is about brittle failure and tension. And also if you are observing the fracture surface, we will be seeing certain V-shaped marks or chevron marks. These chevron marks will help us in assessing the direction of crack propagation. So please do keep in mind, brittle failure in tension gives rise to the riverbed pattern or grainy appearance. and it will be having a flat surface perpendicular to the applied load. Also, we can see chevron or V-shaped marks and that helps us to assess crack propagation. So next is impact fracture. So impact fracture, if you have already studied, I think there is tests known as ISO test and CHARPY test. That particular material will be having a notch and it will be subjected to a very high impact force and the specimen will break. So in case of impact fracture, we can see here it is conducted as minus 196 degrees Celsius and this is conducted at 340 degrees Celsius. So the temperature is going on increasing. So initially the material was brittle. That is why we have a grainy appearance. And as the temperature increases, there is a transition and we have a ductile material. That is why we are seeing dimples. These are actually SEM images of a material that undergoes transition from a brittle nature to ductile nature when subjected to a CHARPY impact test. So now next we have compression failure. So far we had seen about tensile failure, that is where pulling the specimen and it fails. So next is compression failure. And in compression also, depending upon whether the material is brittle or ductile, there will be changes in the fractograph as well as the fracture surface. So in case of brittle material, when we are subjecting it to compression, what happens is that at 45 degrees to the applied compression, it will shear. But in case of a ductile material, when a compressive force is applied, what happens is that it will start to buckle. And if you see both of these kinds of surfaces under a microscope or a same image or whatever, we can see from B1 to B4, this is the fracture morphology of a brittle material under compression. And here is the fracture morphology of a ductile material under compression. So this is ductile fracture in compression, this is brittle fracture in compression. So here please keep in mind that buckling takes place for ductile materials, shear at 45 degree takes place for brittle materials. So the next is fatigue failure. So fatigue failure means that the material will be subjected to repeated cycles of stress, and due to these repeated cycles of stress, eventually at particular number of cycles the material will fail. So initiation of the cracks takes place at this point. The crack propagates and it becomes a fast fracture. So that is why we have these beach marks. Similar kind of beach marks are obtained in this image also. Therefore, progression marks or beach marks that denote crack growth are obtained in fatigue failure. And if you see the fracture surface of a material that has undergone fatigue failure, we can see that these kinds of structures can be seen. These are actually ratchet marks. That is, these ratchet marks are obtained at the boundary between two adjacent failure planes. And I've also mentioned that in fatigue failure, the material will be subjected to repeated cycles of stress. So what these kind of striations are obtained in a material due to the repeated cycles of stress. So please note, in case of fatigue failure, things to notice that the ratchet marks will be there, beach marks will be there on the fracture surface. So this is under microscope, this is the macroscopical view, and finally if you see under SEM or TEM, if you see under SEM or a microscope, we can see that these are fatigue striations. So I hope that clear. Now we will go back to our question. Beach marks are commonly observed on the fractured surfaces of metal after a fatigue failure. So that is the answer to this question. I hope it's clear for all of you. So with that, let us move to the next question. At equilibrium, the maximum number of phases in a three component system at constant pressure is. This is a very direct question. It was asked in GATE Metallurgical Engineering 2018 for 2 marks. Please note that very simple question for 2 marks. So please be familiar with these kinds of concepts. So in order to solve these questions, we need to understand what is meant by a Gibbs phase rule. So the Gibbs phase rule gives the number of phases that will coexist in a system at equilibrium. So the Gibbs phase rule is given as F plus P is equal to C plus N. So what is this F, P, C and N? So first is P. That is what is asked here. That is the maximum number of phases that can coexist. C is the number of components in the system. And N is the number of non-compositional variables like pressure and temperature. F is the number of degrees of freedom or the number of externally controllable variables which can be specific, which should be specified to define the state of the system. and these can be changed independently without altering the state of the system or without altering the phases that exist at equilibrium. So here we are asked to find the number of phases given that the system is in equilibrium, and the number of components is given, and the number of non-compositional variables is also specified. So here we can say maximum number of phases we have to find. It is a three component system, so therefore C is 3, and it is at equilibrium, therefore number of degrees of freedom is 0. And also the system is at constant pressure. Usually when there is both temperature and pressure, N should be equal to 2. But in our case, since pressure is constant, we are taking N is equal to 1. So what happens at equilibrium? F is equal to 0, three component system at constant pressure. 0 plus P is equal to 3 plus 1, which gives P is equal to 4. So I hope the concept is clear to all of you. Just F plus P is equal to C plus N. F0, P we have to find. C is given as three component system. Pressure is constant, therefore N is equal to 1. If it is not mentioned that the pressure is constant, it should be N is equal to 2. That is the difference. So therefore the answer will be 4. I hope it's clear for all of you. Now we'll move on to the next question. If the net magnetic moment of an iron atom in BCC structure is 2 mu b, then saturation magnetization of Fe is, it was asked in GATE Metallurgical Engineering 2018 for 2 marks. So we have to find the answer in kiloampere per meter up to 1 decimal place. And we might be wondering what is the value of mu b. Here mu b is given as 9.273 into 10 power minus 24 ampere meter square. And also lattice parameter of BCC ion is given as 0.287 nanometer. We might be, now we don't know why lattice parameter is misread. So once we define what is meant by net magnetic moment, what is meant by magnetic moment, saturation magnetization, etc., we will be understanding why these parameters are given in the question. So let us read the question once more. If the net magnetic moment of an iron atom in BCC structure is 2 mu b, then saturation magnetization of Fe is. So here it is given that net magnetic moment is 2 mu b. So what is meant by mu b? Mu b is the magnetic moment of one electron spin. So if mu b is the magnetic moment of one electron spin, net magnetic moment would mean that it is the summation of magnetic moment of all electron spins considering their signs. That is given as 2 times mu b. Mu b is the magnetic moment of one electron spin. Net magnetic moment means summation of electron spin of all the electrons present in the atom considering their sign. And what is meant by saturation magnetization? So the most important part of this question, the equation for saturation magnetization. Saturation magnetization is defined as the ratio of total magnetic moment per unit cell divided by volume of unit cell. So now you might be understanding why lattice parameter is given. Using lattice parameter, we can easily find the volume of the unit cell. And we have to find out the total magnetic moment per unit cell. Here, the magnetic moment of one atom is given as 2 times mu b. We know that in BCC structure, there are 2 atoms per unit cell. Therefore, the total magnetic moment per unit cell will be 2 times 2 mu b. है We know there are 2 atoms in BCC unit cell. Therefore, total magnetic moment per unit cell is 2 times 2 mu b. And it is also given, the lattice parameter was given to us, volume of unit cell is therefore given by A cube, that is equal to 0.287 nanometer the whole cube. And if we take the ratio of this by this, we will get what is the saturation magnetization. And also in this question, it was already mentioned that the unit has to be Ka per meter. So in order to verify that, we can just divide these two things. That is 2 times 2 mu b by A cube. 2 times 2 mu b will have a unit of A m square. And A cube will be having a unit of m cube. Therefore, on dividing these two things, we will be getting A by m itself. So 2 times 2 mu b divided by a cube, a divided by m is equal to 1571.69 A per meter. So that is the saturation magnetization. So in this question, very important, please memorize this particular equation. Saturation magnetization is equal to total magnetic moment per unit cell divided by volume of the unit cell. And whatever, please read the question very carefully. Please remember number of atoms in BCC, FCC and so on, and then connect using the equation. That is how you will be able to solve such kind of a question. It's actually just remembering one equation and you'll be getting 2 marks. So please try to revise these kinds of concepts. I hope that's clear for all of you. And now let us move on to the next and final question. In a powder diffraction experiment on BCC ion, the first peak occurs as 2 theta is equal to 68.7. The wavelength of X-rays in nanometers up to 3 decimal places is dash, and lattice parameter of iron is given here also. So if people, some of you may have already conducted XRD experiments as part of your research, so you might be knowing whenever we give our sample for XRD, you will be getting a graph of intensity versus 2 theta, right? And based on the structure of our material, the points where these peaks occur will be specific locations. It won't be some random location. And from these specific locations, we will be able to identify, okay, my material is in BCC, my material is in FCC, or maybe material has so and so phase and so on. So here it's mentioned that I have a BCC ion and my first peak I got at 2 theta is equal to 68.7. But I actually will be knowing the wavelength of X-rays, but the question is that we need to find the wavelength of X-rays from the given data. So in order to understand this, first, we need to know what is meant by extinction rules, or what is the allowed and forbidden intensities in X-ray diffraction. So that is given from this thing. So here primitive any HKL combination is possible. In BCC, H plus K plus L is equal to 2N, that is it should be even. So face centered means HKL should be odd or all even. FCC diamond means HKL should be all odd, and if it is even, then their sum should be equal to 4 times L. And in HCP, L should be even, H plus 2K should not be equal to 3 times L. So in that case, in our case, what in our question, what is mentioned? Powder diffraction experiment on BCC ion. BCC ion, the constraint is that H plus K plus L should be equal to even. So think of the first combination that gives it HKL is equal to 2 times N. If N is equal to 1, then in that case, N is in n is a natural number. So h plus k plus l should be equal to 2 times of n. So what will be the first combination? We can substitute as h as 1, k as 1 and l as 0. And if we are having a combination of Miller indices as 1, 1, 0, it will satisfy our even criteria, right? 1, 1, 0, 0, 1, 0, 1 or 0, 1, 1. So the first combination that comes to us is 1, 1, 0. Therefore, the first peak of BCC occurs on the plane 110. That is the first and foremost thing that we should know. This 110 will help us in finding the rest of the answer. So that is done. So I hope till this part it is clear. We need to identify the extinction rule. Try to keep in mind these values at least for BCC and FCC. I won't ask you to remember diamond cubic structure or HCP or anything. Just primitive BCC, FCC. These allowed reflections, if you keep in mind, it will be very helpful because I've seen such questions being repeated. So from this extinction allowed reflection rules and allowed reflection, we found out that the first peak for BCC occurs on the plane 110. That is our first hint. So HKL values we have obtained. Now we will be using two more equations to solve that particular question. So the first equation that we'll be using is Bragg's law, and the other one is the equation for the interplanar spacing. So from Bragg's law, we know that n lambda is equal to 2d sine theta, where n is the order of reflection. Usually for problem solving, we will take n is equal to 1. So like why n is equal to 1 is a discussion that is pertains only to Bragg's law and diffraction. So in case you people have any doubt, please do email me. I'll try to include it in my next lecture. So n lambda is equal to 2d sine theta, and suppose we are considering order of reflection as 1 and lambda is wavelength, we have lambda is equal to 2d sine theta. Theta, 2 theta value we already know 68.7, from that we can get theta value. Now the question that we need, now the thing that we need to find is d value. D is the interplanar spacing. Therefore, for cubic unit cell, we know that d, the interplanar spacing, is equal to a divided by root of h square plus k square plus l square. HKL values we had already identified previously, right? 110. Suppose you are substituting the lattice parameter of ion A is equal to 0.287 as A and HKL as 110, then we will be able to find the value of D. Here A is 0.287, 2 theta is equal to 68.7, so divide by half, we will get theta value as 34.35 degrees, and D is equal to A divided by root of h square plus k square plus l square. So on substituting, 0.287 divided by 1 square plus 1 square plus 0 square, that is 0.203 nanometer. And if this D, we substitute in this equation, we will get our lambda value. Therefore, lambda is equal to 2d sine theta, 2 into 0.203 sine 34.35. Therefore, our final answer will be 0.230 nanometer. Please note that here in nanometer to 3 decimal places, and whenever such things or constraints are mentioned about the answers, please do stick to the constraint, because if your answer does not match the constraint, you won't be given any marks even if your value is correct. So if they are mentioning 3 decimal places, please do include 3 decimal places, and even if that is a zero, you have to add zero. So therefore the final answer is 0.230. So I hope all of you have understood all four questions that we had discussed today. So please try to include more of yourself in these interactive sessions. Keep asking your doubts, and whenever you don't feel clear about a particular concept, you can interrupt me anytime. I'm also a student as yourself, so please do interrupt me at any time. We can discuss, and in case we can not able to find a particular concept, we will brainstorm and we'll make it a highly interactive session. I know gate preparation is quite monotonous and it's a very, you'll be under a lot of pressure, but this interactive session is actually to help you break out of that. You have help at our end, so please utilize these help. And you have multiple live sessions throughout the week. Find time to spare just 1 hour, and I hope to meet you all on Thursday next week, 6 p.m. to 7 p.m. So in case you have any additional queries or doubts, or if you want any particular topics related to gate, please do email me at santra.pmrf@gmail.com. So that's all of it for today. Thank you so much, and thank you. Bye bye.